Hello and welcome to Cumulative Review number 5 for second semester. We're going to start off mostly in Unit 10 on this first page. So starting off, it says rewrite log base 10, because there's no 10 there, there's no number there. We assume that that's the common log with a base of 10 of x is equal to 2 in exponential form. So remember, writing in exponential form means you need to have something that's in an exponent. So to undo a logarithm, we're going to use a base of 10 on both sides. We get x equals 10 to the second, and we stop there. I know it's tempting to want to say x equals 100, but if we wrote x equals 100, we would not be in exponential form. Next one, rewrite e to the x equals 8 in logarithmic form. Logarithmic form means that we need to have a logarithm involved. In our case, we're going to use the natural log because the natural log will undo the e base for our exponential. So natural log and e cancel out, and you're left with x equals the natural log of 8. That's your final answer in logarithmic form. All right, next set says to evaluate, which means we are looking for a value, right? The word value is inside of evaluate. Show your work and logic for how you arrived at your answer. Well, that's the whole purpose in making this video, so I will definitely show that. A logarithm asks the question, what power? What power? So I'm trying to say 3 to what power gives me 81. So what I'm asking is 3 to what power is 81? In this case, that's going to be 4. The other way you can think about it is to say log base 3 of 3 to the 4th. 3 to the 4th being 81. Log base 3 and 3 cancel out, and you're left with 4. Next one, 2 to what power gives me 1/8. That's going to be -3. You also could think log base 2 of 2 to the -3rd. Then log base 2 of 2 will cancel. That -3 swings down, just like this 4 would have swung down. We're good to go. Last one, 5 to what power gives me 1. Well, that's going to be to the 0 power. You also could think that log base 5 of 5 to the 0, 5 to the 0 being 1, those will cancel out. 0 swings down, we get 0. All right, condense the logarithmic expression to a single logarithm. The word single is bolded because we're trying to get our final answer to be just a single logarithm. In this case, we have a log with a base 10 in all 3 of our terms, so we'll be able to combine like terms. We want to go backwards in our properties of logarithms from what we learned. So we learned last to swing down 1/4, so I'm going to swing the 1/4 up, I'm going to swing the 9 up, and I'm going to swing the 3/4 up. And what I mean by that is I'll end up with log x plus 1 to the 1/4 minus log y minus 2 to the 9th minus log z to the 3/4. Next thing that I want to look at is, do I have things separated by addition or subtraction? Well, in this case, I've got 2 subtractions. Subtraction turns into division for us. So I'm still going to have that single logarithm. In the numerator, I had a positive x plus 1 to the 1/4. The denominator is what I get from my negative terms. So this will be y minus 2 to the 9th times z to the 3/4. Now, technically I have met my criteria that I have a single logarithm, but I also could go a step further and see, is there anything in there that I could kind of clean up? And so something I could clean up is I could rewrite this as a 4th root. This can't really do anything about, don't have to multiply that out 9 times. This I could write as a 4th root of z to the 3rd if you really wanted to. But again, this line meets the criteria of having written as a single logarithm. All right, so when we were condensing, we undid our exponents, then we undid our addition and subtraction. When we are expanding, like in number 5, we want to expand with addition, subtraction first, then swing down our exponents. So I'm going to look to rewrite this as log base 4 of x to the third y to the sixth over z, all of that to the 1/2 power because of this square root. So what I can do is I can swing that 1/2 down. Then I'm going to have log base 4 of x to the third plus log base 4 of y to the sixth minus log base 4 of z. Well, each one of these gets a 1/2. So I'm going to distribute that 1/2. Oop, that's a minus sign in there. Log base 4 of z. Finally then, I can swing the 3 down and the 6 down. So I'm going to end up with 3/2. Come on, pen. I'm going to end up with 3/2 of log base 4 of x plus 6 times 1/2 gets me just 3 log base 4 of y. This one I only had a 1 to swing down, so that really doesn't do much, minus 1/2 log base 4 of z. That's a log. Keep in mind there are other ways to do this one. You could have started by applying this 1/2 exponent to the 3 and making this a 3/2 and this a 3 and this a 1/2, and then you don't have this here and you swing those down. I would really encourage you to go back to section 10.4 if you are feeling stuck on logarithm properties. There was the one video that was required, and then there was an optional practice video. And so if you're feeling like maybe you need more practice on this topic, please be honest with yourself and go back and rewatch section 10.4. All right. Solve each equation in numbers 6 through 9, leave exact answers, or round to the nearest thousandth, so 3 decimal places. Be sure to check for extraneous solutions. A reminder with logarithms and exponentials, you need to check for extraneous solutions when you have a logarithm, because your log domain is that x has to be greater than 0. So that's going to dictate that we have a domain problem, so we need to check for extraneous answers. All right. Number 6 and number 7 are both exponentials. If you look at your list of how to solve an exponential, the first thing you want to try is to rewrite in the same base. So I noticed that 8 and 32 both can be written as a base of 2. 8 being 2 to the third, 32 being 2 to the fifth. And then this is still 5x plus 1 and x minus 3. The next thing then, when you have a power raised to a power, is you multiply. So 2 to the 3 times 5x plus 1 equals 2 to the 5 times x minus 3. Well, that means 2 to the 15x plus 3 equals 2 to the 5x minus 15. And since I have a common base, it means whatever is in the exponents must be equal to each other. So 15x plus 3 has to equal 5x minus 15. If you go through and solve this, you get 10x equals negative 18. X itself is equal to negative 9/5. Right? So that's one way to do that problem. I think that's the most efficient way to do the problem, and math is about being efficient. You could also do some work with logarithms, but I would encourage you to rewrite with the same base. Otherwise, you could take a natural log of both sides, you could take a common log of both sides, you could take a log base 8 of both sides, you could take a log base 2 of both sides. But again, the first thing with an exponential that you want to try is to see if you can rewrite in the same base. All right, number 7. I need to isolate my exponential. So I'm going to start with 3 times 7 to the x minus 7 is now equal to 39. Peeling away another layer, undoing PEMDAS. So remember, PEMDAS is how you simplify, but you go SADMEP when you are solving. Okay, so I got rid of my addition. Now I'm going to get rid of my, I don't have any subtraction. I'm going to get rid of my multiplication. So I'm going to end up with 7 to the x minus 7 equals 13. Now I'm going to get rid of my exponent. Well, how do I get rid of an exponent? I take a logarithm. If you have the new fancy calculators, then you want to use a log base 7 of both sides. These will cancel out. You're left with x minus 7 equals log base 7 of 13. X equals log base 7 of 13 plus 7. You want to keep parentheses around that 13 so you don't accidentally write log base 7 of 20. Okay, so that's if you have the new fancy calculator. And when you do that in your calculator, if you have your change of base formula in there, you should get a decimal approximation of 8.318. But let's say you don't have that fancy new calculator. That's fine. When you get to this moment, instead of taking a log base 7, just take a natural log. Swing that x minus 7 down in front. And now continue solving for x. So we'll get x minus 7 equals the natural log of 13 divided by the natural log of 7. And then I add 7 to the other side. This would also be a totally fine answer. If you put that in your calculator, you'll get the same 8.318. All right, logarithmic functions. You want to start by condensing with properties of logs so that you can use a single logarithm, undoing it with an exponential. So this addition between my two logarithms, before I can 8 both sides, I need to condense to a single log. Addition is going to turn into multiplication. So I'm going to end up with log base 8 of x times x plus 12 is equal to 2. Now that I have a logarithm, a single logarithm, I can undo that with an exponential of a base 8. Those will cancel. I have x squared plus 12x equals 64. To solve a quadratic, I want to set everything equal to 0. And a factor, I end up with x plus 16 and x minus 4 being equal to 0. X equals negative 16, x equals 4. But I need to check because I started with a logarithmic equation. I need to check if I sub in negative 16 to the typed original equation before I've done any altering to it. I end up taking log of negative 16, which I can't do. So this is illegal, extraneous. If I go through and I sub in 4, so if I try 4 into my equation, I get log base 8 of 4 plus log base 8 of 4 plus 12, which is 16. This one ends up working. This is my good one. Negative 16 was extraneous. All right, similar concept here. So this time I have subtraction, so I want to get things in a single logarithm. Changing subtraction into division. In order to get rid of this log, I used an exponential with a base 8. Here I'm going to use an exponential with a base of e. So my pre-calculus teacher used to tell me to e both sides. E to the third. Well, then I'm going to use some careful solving. This will be e to the third times x plus 1. Multiply both sides by x plus 1. Okay, and then I'm going to divide by e to the third. That'll be equal to x plus 1. And then I get 5 over e to the third minus 1 is equal to x. If you take this and type it into your calculator, should do that real quick. 5 divided by e to the third minus 1 is negative 0.751. If we round, negative 0.751. So I need to take this and I need to sub it into the original to see if it works. Now, just because it's negative doesn't mean we throw it out. If I take this and I sub it in, I get a negative 0.75 plus 1, which is a positive number. So this does, in fact, work in its exact form or in its decimal rounded form. So again, to undo an exponential, you want to try to rewrite in the same base. If not, use logarithms. To undo a logarithm, you need to condense to a single log and then use an exponential to undo.